Assalamu alaikum wa rahmatullahi wa barakatuhu, and good morning to each and everyone present here. It's my pleasure to be a moderator for webinar. I would like to extend a warm welcome to all of you. Before we proceed to the session, let us invoke the blessings of Allah subhanahu wa ta'ala. I request Miss Maryam Mufida and Saliha Fatima to recite a few verses from the Holy Quran and to render its translation.
Assalamu alaikum. أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. والتين والزيتون وطور سين وهذا البلد الأمين. لقد خلقنا الإنسان في أحسن تقويم ثم رددناه أسفل سافل إلا الذين آمنوا وعملوا الصالحات فلهم أجر غير ممنون. فما يكذبك بعد بالدين أليس الله بأحكم الحاكمين.
Translation. I seek refuge in Allah from the accursed shaitan. In the name of Allah, the most beneficent and the most merciful. Surah Teen, the fig. By the fig and the olive, by Mount Sinai, and by this city of security, Makkah. Verily, we created man of the best stature. Then we reduced him to the lowest of the low. Save those who believe and do righteous deeds. Then they shall have a reward without end, the paradise. Then what or who causes you, O disbelievers, to deny the recompense, that is the day of resurrection? Is Allah not the best of judges?
Jazakallah khair, Ms. Mufida and Saliha. To begin this program, we are pleased to have Ms. Aisha Mubashara to deliver the welcome speech.
Assalamu alaikum and very good morning to everyone present here. It gives me immense pleasure to welcome you all for today's webinar on the topic application of Hill Cipher and RSA, that is Reverse Shamal Agreement Crypto System. First of all, I would like to welcome our respected correspondent, Mr. Faizur Rahman Said sir, Madam Principal, Dr. Shahnaz Ahmad, Vice Principal, Dr. Amatul Aziz ma'am, Head of the Department, Mrs. Sabira Parveen ma'am, other faculty members, and my dear fellow students. I extend my sincere welcome to our resource person, Dr. A. Felix sir. He is an assistant professor in the Department of Mathematics in the School of Advanced Sciences, Vellore Institute of Technology. He has completed his BSc Mathematics, MSc Mathematics, MPhil in Mathematics, PhD in Mathematics at Loyola College, Chennai. He has 10 years of teaching experience. He has researched in fuzzy model and its applications. He has got many awards. Best Paper Award and cash prize in the International Conference of Mathematical Science held at Satyabama University, Chennai. Sam Warrior Endowment Fellowship for the outstanding percentage of mark in MPhil by the University of Madras. Maulana Abul Kalam Azad National Fellowship Award by UGC for doing PhD research program. Young Researcher Award for Fuzzy Model by IIR Chennai for the year 2017 and Outstanding Scientist Award by VD Good Technology Factory in the 12th International Scientist Award on Engineering, Science and Medicine. He currently guiding 6 PhD students. He has published 49 international journals and 3 books on the topics Latin Square Design and their application, preparatory course for RCSC examinations, and Reminiscences and Remembrance of Francis Charles Rsi. He has been a sub-editor for International Journal of Data Mining Techniques and Applications and International Journal of Business Intelligence. He has been a coordinator for 2 workshops organized by VIT, and he has organized 4 international conferences. We are extremely delighted to have you today, sir. Now, I welcome Dr. A. Felix sir for the webinar on the topic Application of Hill Cipher and RSA Crypto System. Over to you, sir.
Thank you, Aisha, for your nice introduction about me. And first of all, let me thank the management of Justice Bashir Ahmed Saeed College for Women and the management of this college, the secretary and correspondent, principal of this college, head of the department, Mrs. Sabira Parveen, and the organizing secretary of this event, Dr. M. Rihana Praveen, for giving this wonderful opportunity to interact with you all. So always, as I said, it is really joyful to interact with the students, okay, though it is the online mode, and I always enjoy to interact. Thank you so much. And the title of today's talk is on applications of Cipher and RSA Crypto System. Okay. Whenever we want to send a message to anybody, to our friends or anybody, we feel that it should be secret. The same way, anything to keep it secret, we need some secure, isn't it? So those days, to send the message, anything secretly, without breaking by third person, there are a lot of things they've made. Okay, so for instance, those days when the war was going on, suppose a king wants to send a message to the marshal, the captain of the soldier, marshal. So what he will do, he will choose a servant, the reliable servant. He will shave the head on the servant, and then something would be written, some message would be written on a set, and he has to write till the hair comes back to the original question, and then the servant would be sent to where the war is going on. Suppose if he's caught by the opponent kingdom, so it is really, they won't suspect something is written on the head, so they will check and then they will leave. And ultimately the servant would reach the place where the war is going on. The marshal would read the message and he will go ahead what the king has been instructing to him. Okay, this is how they will send the message secretly. But still it is not safe, right? Those days they want to send any information. They've used the DAO and so much of things, this kind of servant, but it is not a secret. Okay, and instead, can we use any mathematical concepts of sending a message secretly? Okay, so in 1729, the mathematician called Leisure S. Hill, he introduced the concepts of Hill cipher, and then this slowly, they've enhanced the crypto system, that is the RSA crypto system. 3 mathematicians who joined together and created this crypto system. Therefore, the first letter of their name is kept named as RSA crypto system. These are the 2 interesting things that we are going to see. And if you look at the crypto system, the base, okay, the heart of the crypto system, definitely the linear algebra and the number theory. So this Hill cipher would be dealt by definitely by the linear algebra and your number theory. Okay, so before let's go into the concepts of Hill cipher and RSA crypto system, we need to understand the linear algebra and number theory. Okay, let's have a look. Okay, so what is a linear algebra? Okay, so linear algebra is a study of vectors and linear transformation. Okay, and whenever I look at this linear algebra, something is coming to mind always. When I was something 7th standard I was doing, at the time, one of my the grandparents who were at my village, he posed this puzzle to me. Okay, usually, whenever I take this linear system of linear equation or linear transformation, I used to tell this. Okay. So what he did, he gave 100 rupees to me. The puzzle goes like this. He gave 100 rupees to me. He asked me to buy the 100 goats. Okay. He asked me to buy the 100 goats exactly. In the market, the male goat is 10 rupees, female goat 5 rupees, and baby goat is 50 paise. Then how many male, female, baby goat I would buy so that I would get exactly spend in 100 rupees exactly. I should not have any remaining 100 rupees. I should also buy exactly 100 goats with a combination of male, female, and baby goat. This is the puzzle he has posted to me. And frankly speaking, I was not able to answer for his question. He gave me some 1 hour timing. I was doing all such table calculation, whatever we have learned at our lower classes. All the tables I was thinking, and ultimately I could not give the answer to him. And he challenged me, if you are answering, I'll give 100 rupees to me. But I couldn't do that. But after 1 hour, he gave me the answer. Okay, you can also think it over, but I'm not making you to solve, because only 1 hour is there. With the 1 hour, I want to tell something. Okay, so the answer is, you would buy one male goat, 1 tens are 10, and then 9 fives are, what is it, 45, and then this is, what is it, 45, 90 baby goat I need. 90 into 55 say is 45. So altogether, this is 100, this is 100. So I can get exactly 100 goats. I was thinking how this could be done. Some logic is there. He did it logically. But once I came to the mathematics, I was opting the mathematics. I was thinking about this, how this situation can be represented in terms of an equation. So what is said? The first thing is, if you take it male, female, baby goat as x, y, z. Okay. So what is it? The first question, the first condition is said this: the sum of male and female, all the goats should be 100. X plus y plus z is equal to 100, isn't it? And then another condition, I must have spent 100 rupees exactly. I should not have remaining anything. The first one is number of goats and the cost. The second equation talks about the cost. What is it? 10x. Male goat is 10 rupees, female goat is 5 rupees, and then this is 55, say, baby goat. This count should be 100. So whatever he said, that I was trying to give it in terms of an equation, x plus y z is equal to 100. And then, we have learned the system of linear equation, right? Ax is equal to b, system of linear equation. Linear equation, system of linear equation, in the sense you have a set of linear equation with the same unknowns. Okay, you have a set of linear equation with the same unknowns. This is what Ax is equal to b. Here A is the coefficients of the unknown. Here the coefficient is 1, 10, 1, 5, 1, 0.5. Isn't this is the coefficient matrix A, and x would be the unknown variable x, y, z, and this one b is the right hand side constant value. Okay, so I was thinking, and we have learned in our lower at your undergraduate and postgraduate you're learning, if you solve the system, you will be getting, what is it, unique solution. The possible solution are unique, and then no solution, infinitely many solution. Under what situation you can have infinitely many solution, no solution, unique solution, and all, you would be learning. It's all about, you would be talking about your matrix. If the matrix is non-singular, then you can have a unique solution. If it is a singular matrix, I mean determinant is 0, you can have either no or infinitely many solution. These are the things that you would be learning. But look at this here, you have what is it, 2 equations and 3 unknown variables. 3 unknown variables are there, x, y, z. 3 unknown variables are there. Okay, in this situation, one variable can be the free variable. Okay, rest of the 2 variable are the basic variable. One can be assumed as some value you will be assuming. The xy would be depending on your whatever the value that you're giving your z. So therefore, in the situation, you can have infinitely many solutions. Okay, when the number of equations less than the number of variable, then you can have infinitely many solutions. The one such solution he gave to me is 1990. If you solve this system, you can have infinitely many solutions. Since the goats are living things, we always give in terms of the positive integer form. So this is a one such solution. Okay, so this Ax is equal to b alone, this ill cipher has taken to give the cryptography. Okay, So what, we should not view the matrix as a matrix. In school, we were taught that matrix is the set of all the arrangement of numbers in the rows and columns. But we should not be the mathematics students. We should not view that in terms of what we have learned in lower classes. You should look in the different aspects. So whenever you are gaining the knowledge, the way of looking the concept should also be in the matured form. Okay, so the matrix should be viewed as the transformation. Okay, so you can view the matrix as the set of all column vector. You can view them as the column vector. If you are pursuing the linear algebra, you should start to view the matrix as the set of column vectors, set of all column vector or set of all row vector, which would act as the transformation. Okay, so this Ax is equal to B is the Hill cipher is taken, Hill is taken to create the crypto system. Okay, fine. So Ax is equal to B. So A would be the matrix. Whatever the vector, the solution vector, if you transform through this matrix A, you will be getting your B. So look at this here. A would be, what is this? This is your 1, 1, 1. This is 10, 5.5. And the unknown variable X is X, Y, Z. And B is 100. Okay, if you transform this vector through this matrix, you'll be getting your 100. So what this XYZ? So 1, 9, 90. If you transform this, you will be getting this 100. Okay, so here we will be viewing this matrix as the transformation. Okay, fine. Linear transformation, you know this. So linear transformation, you take any transformation is linear. You take here, we will be using two addition, vector addition, scalar multiplication. That I'm not going to deal. Okay, scalar multiplication you will be taking. These are the two terms you will be taking. This transformation also holds this linearity. Okay, then we can call them as a linear transformation. But this is for your understanding. Okay, anyhow, we don't want to spend much here. Okay, so let us come back. The cryptography, our topic. So crypto in the sense we want to send a message secretly to the person, okay, without breaking by the third person. So that is the cryptography. So the study of encoding and decoding secret messages is called the cryptography. So what is the meaning of this encoding and decoding? Okay, suppose I want to send the message. This is the message. God is love. This is the message I want to convey to everybody. Okay. So how I can make it? Okay, this is the plain text, right? This is the plain text. If I send this message to all of you, this can be easily broken. Some secret messages I want to send. If I do this, then what will happen? This everybody can read it. So this is the plain text. Instead of sending this, I can use some operation here and change this into something. Okay, that is called, what is it? Cipher text. Okay, cipher. Okay, cipher text. So what we have done, the plain text is converted into the cipher text. Even in lower classes, you might have played with something. Suppose this is the thing that we have, maths. Okay, so what you used to do, A, B, C, D are represented as the number 1, 2, 3 something. You know the M position. M, what is it? M plus 3. You will be adding some 3 numbers. M plus 3, and whatever you are getting, that you will send it to your friends, whether they are able to break this or not. In school, definitely you would have played this kind of game. Okay, so plain text is whatever the text you have, something you are using, something addition of the plain text or subtraction of something you will be using. That text is called the cipher text. Okay, now the conversion from plain to cipher is the enciphering. Okay, the conversion from plain text to the cipher is the enciphering. From cipher text to the plain text is the deciphering. So encryption is, enciphering is from plain text to cipher text is the encryption, enciphering. Okay, from cipher text to the plain text is decryption, deciphering. Okay, this is we need to understand. Okay, fine. And as I said initially, I also said those days how they have sent the message secretly. They everyone will have the reliable servant, reliable people. They will keep it. They will send the message. Even whatever you do, they won't reveal that. Okay, or if a person, if something king wants to send the message, what the servant head would be shaved and write something on a set, and it would be sent to the marshal. The marshal will go ahead whatever is being instructed. Okay, that is the one way. And then this kind of skytle. Everyone will have this kind of scale or ruler, and they will rotate a paper or cloth, anything, and they will write some message in a one side. Suppose this is the message love. This is the message I want to send. Okay, this is the message I want to send it to the people. Okay, so we are all here to, you know, to love each other. Okay, so this is the message I just want to convey. So what I'll do, I'll send this LOV one side, and the remaining part, you know, the empty space would be right, correct? So if you write one side, you can have this. In another side, in the empty spaces, you can fill it C, X, Y, Z, something. Okay, this is sent to somebody. Okay, what he will also have this kind of ruler, this kind of title. So he will rotate, and he could see what is the message. At one side, you would be able to see what the message has been conveyed. This is called skytel. Those days, this is also being used. Okay, but still, this is not a safe. If everyone have this kind of ruler, then easily the message would be broken. Okay, so instead, what we can do, can we use the mathematical ideology so that it is really tough for the people to break it. Okay, suppose here this is the plain text A, B, C, D, F, G, X, Y, Z. This is the plain text. Okay, so now what we have done, the plain text plus 3. Okay, so cipher text, this is equal to, what is that, P plus 3. Okay, so what will happen? So sub A plus 3 plus 3, what is that? D will be getting. B plus 3, E, F, G, something. Suppose this is the message, Joseph. This is the message, yes, I want to send it. So look at the J position, J plus 3. J, where is that? J plus 3, M, and then O, O plus 3, O plus 3, R. Similarly, C, P, H. If we take H, yeah, H plus 3, K. So this is the message I can send it. Suppose this is the message I want to send it. Okay, Joseph, I want to send it. Okay, the cipher text MRVHSK. Okay, this is the cipher text. Suppose I want to get back the original message. How can I do this? This is the, what is it? Encryption. Suppose deciphering, decryption. How we can do this? Decryption. Okay. So this can be done. What is it? F of C, C minus 3. So this is nothing but your P. Okay. P is equal to C minus 3. The inverse of 3 would be taken under addition. Okay. C minus 3. Look at this, M minus 3, J. Okay. R minus 3 is 4. Okay. We are able to get back the message, Joseph. Still, you know, you could find it out some sequence in every pet. In this, you are able to find it out the pattern. Okay. This message is conveyed with any pattern, any sequence or not, that we are able to pursue with that. Still, this is not a safe, isn't it? Instead of this, what we can do, you can, the given name can be factorized into the n terms. Suppose this Joseph you had only one way you have done it. Instead of this, what we can do, you can divide them into pair or divide them into 3 elements, like this you can convey. Okay, so this is called the polygraphic. Okay, Joseph you have, suppose instead of sending single letter encryption, you can make it the pair. Okay, here I have made it as the word is divided into pair of elements, or you can also make it as the 3 elements. Okay, 3 elements you can make it. Suppose 3 elements is not, and then 4 elements you are dividing. Okay, so 4 you are making. So here you are not able to make a 4, where you can add some dummy variable. So ph is repeated. Okay, like this you can divide and send the message. This is called polygraphic. Okay, this polygraphic concept is applied in the matrix form, and then bring it out the cryptography. That is ILS. Okay, as I said, suppose the king, this is Caesar crypto system. King, Caesar wants to send the message to the soldier attack. Okay, so if we send the message directly, easily this message would be broken. Instead, what he does, he used something. Okay, plus something he has used, plus 3 or something, and this is the message the soldier carried to pass the information to the marshal. Okay. So as I said, the encryption from plain text to ciphertext, and then plain text to the ciphertext to the plain text is the decryption. Okay. So everyone will have a key. Okay. So the three I've used three, right? That is nothing but our key. So as how we have a phone number, email ID would be the key. Okay, that is the public key. Okay, the password would be the private key. Okay, so everyone will have a key. So we know you know the key, but it is really tough for us to find it out the inverse of the key coming back. So you can go and you can go this, but coming back is not an easy. So that can be done through the inverse. The inverse, it is really difficult for to find it out. Such a way you will be making. It is we can find it out the inverse where there is a way. Definitely there is an alternative way, but the alternative way should not be known so easily. Okay, so if it is really tough to make the inverse, then what will be? Then it is really difficult for them to break the message. Okay, fine. Okay, so here the the alphabets are assigned a numeral value 0, 1 till 25. Okay, 25. So here the modular arithmetic concepts are being used. Let me give a small introduction about the modular arithmetic. Okay, so in number theory, or if you're not studying, but anyhow, let me give some 2 to 3 minutes I can spend here. Okay, so modular arithmetic, here two types of modular arithmetic. We can additive modulo, mod, and then multiplicative modulo. Okay. And then another one is congruence modulo. Okay, congruence modulo. But here we will be using the congruence modulo. So you can fix some positive integer. N would be the positive integer under mod n. Okay. So here, since we are using 26 alphabets, therefore we are fixing the modulo 26. Okay. Suppose here you will be taking any two numbers, add any two numbers. Okay. Add them, and the resultant would be divided by 26. Whatever it leaves a remainder, that would be the additive modulo n. Okay. Suppose, for instance, let me take n is equal to 5. 6 plus 7 under mod 5. 6 plus 7 is 13. 13 is divided by 5. It leaves a remainder 3. This is what the additive modulo. Similarly, you can do the multiplicative modulo. What is it? 6 into 7. Let me fix n is equal to here 5. Okay. What is that? 6 sevens are 42. So 42 is divided by 5. What is the remainder? 42 is divided by 5. It leaves the remainder is 2. Okay. 42 is divided by 5. It leaves a remainder 2. Okay. This is the multiplicative modulo n. Understand? Additive modulo and multiplicative modulo n. Okay. The congruence modulo n, a comma b is two positive integer as we have taken. Not positive, any integer. N would be the fixed positive integer. Okay, n is the fixed positive integer. Okay, so here a congruent, b mod n. So which means that when a is divided by n, it leaves a remainder b. Okay, when a is divided by n, which leaves a remainder b. This is equal to n divides a minus b. Okay, that is a minus b is the divisible by n. Okay, or we can write this a minus b, this is equal to, okay, k times of n, where k is the integer. Okay, so a minus b is the multiples of n. Okay, so for instance, let me give an example here. For here, you can take, okay, 15 under mod 7. Let me take here 7. Modulus is 7. Okay, n is equal to 7. Okay, when 15 is divided by 7, what is the remainder it leaves? Sometimes you can also interact so that it would be interesting. Okay, 15 is divided by 7. What is the remainder it leaves? Aisha, are you there? Hello? You can unmute and talk.
1.
Yeah, good. So when 15 is divided by 7, it leaves the remainder. Therefore, you can tell this. What is it? 7 divides 15 minus 7. 15 minus 1. Or 15 minus 1 is the multiples of 15 minus 1 is the multiples of k times of 7. So k could be, what is it? 2. Okay, 2 times of 7. Correct? 2 7s are. So this congruence modulo concepts would be used here. Okay. So under mod 26. Fine. But you could ask me how we can find it out the inverse. Okay, that I can spend it For inverse, I can go along with it, then only you can understand this. But now you understand the congruence modulo. Fine. Now let's go into the IL cipher. Okay, as I said, the message, if you send, this is the message, love, this is the message just I want to send. And if I send it only by taking, this is the plain text, p plus 3, then what will happen? This is easily, you can find it out the pattern. Something is added, the plain text is added by 3. You can easily find it out. Therefore, you can easily break it. Instead of doing, what we can do, you can divide them into pair of elements. Okay, here you are using, what is that? This is the key that you are using. The 3 in the sense, everyone will have some phone number like this. Okay, something. This is the phone number of mine. Some, what is it? Suppose I want to send the message, anything. Somebody wants to send a message to me, then they will use this 3. Okay, plain text plus 3, then I'll be getting the inverse. I know this. Whatever the cipher text I got, subtracting 3, I can get it the plain text. So here, what we are going to do, instead of 3, I'll be making a matrix. Okay, so this I'll be taking into the pair of elements. This, okay, pair of vectors. Okay, so this can be transformed through the 2 by 2 matrix. Suppose here you are going to make into, divide into 3 elements, then you will be making the matrix into 3 by 3. Suppose I have this is the phone number. Okay, 1456. Okay, this is the number, intercom number I have. Okay, so what you can make it, this is 1452. Okay, so this intercom number is made it as the 2 by 2 matrix, 1452. You want to send some message to me. Okay, leave, this is the message you want to convey to me. Okay, so what you're going to make, you are going to make it into the pair. If the odd number terms are there, then you can add the one more dummy index. Okay, this is the message, you can do this. So I know the lth position. Lth position, you can find it out. Lth position is 11. Eth position 4. Similarly, you can find it out. This vector, this is going to be transformed, multiplied through this matrix, transformed through this matrix. And if you are getting more than 26, you are using the arithmetic concepts, modular arithmetic concept, divided by 26, whatever the remainder it leaves, that will be taken. Okay, so the first step, you have to choose 2 by 2 matrix. Okay, this is the matrix. Everyone, consider that everyone will have a 4 number. Okay, this is the 2 by 2, 4. Okay, so 1456, like this, everyone will have a 4 number. Suppose this is the message you want to convey to your friend. Okay, leave or mathematics, maths. This is the message I want to convey. Okay, so you can make them into pair. Okay, so you know the mth question, the 8th question, and then transform them through this matrix. Whatever if it is more than 26 divided by 26, whatever the remainder you are getting, that will be the cipher text. Okay, and then what if you get back the original message? Suppose this is the concept, a x is equal to b. Here, what is that? Here x is the plain text, b is the cipher text. B is the cipher text. This is the encryption. Okay, the decryption here is, we are using decryption, would be, what is it? I need the plain text. X is equal to a inverse b. Okay, by multiplying a inverse on both sides, you can get it. So this is the plain text. When plain text is what is that? Cipher text is transformed through a inverse, I'll be getting the plain text. Okay, the task is, you know this a, but how are you going to find it out the a inverse? Suppose you have here, you have taken a 2 by 2 matrix, some large matrix you are taking. Okay, some n by n matrix you are taking. Is it really easy for you to find it out a inverse? For 3 by 3 itself, we feel really difficult to find it out, the inverse. When 4 by 4, you know, the determinant of the matrix is not easy, right? A is equal to, what is that inverse of the matrix? What is that? 1 by determinant of A into adjoint of A, right? So the inverse is not easy. Even for finding the determinant itself is really challenging task, and then finding out the cofactor and taking the transpose is really, really difficult task. So while finding the A inverse, you know, the message would be reached to the person would finish up the work. Then finding the A inverse would be the really finding A inverse and finding the message, it is weighing for them. Okay, so like this, you are making your matrix so stronger. So you only knows your A inverse because you have taken a lot of effort and finding your A inverse, right? Okay. So encryption is done by AX is equal to B. Here X is the plain text. The plain text is transformed through the matrix. Okay, A would be whatever over the phone number like this. That is, you made it as a matrix. That message is transformed through this A. They will be getting your this plain text, this ciphertext, and then the ciphertext is transformed through A inverse to get this plain text. Fine. So this is what the Hill cipher. Hill has done this. Okay, Lester S. Hill. He proposed this concept 1929. Okay, 1929. Now look at this. As I said, so now this is the message just I want to convey. Okay, so the secret, this is the like phone number. So everyone will have phone number. This is the phone number I have. A someone's phone number. I want to send this message. Okay, so Lth position, you know this Lth position is 11, and then Oth position is 14, 11, 14. So if you transform this, we are getting 262, 263. When they are divided by 26, whatever the remainder leaves, 2, 3. So 2th position is C. Okay, and then Dth position is 3. Okay, 3 is we obtain CD. Okay, so if you transform LO through this matrix, we obtain under mod 26 is 2, 3, that is CD. Next, take another set of letter V, love. So V position is 21, Eth position is 4. Okay, so if you transform through this matrix, this is we obtain under mod 26, 16 and 5. 16 is, what is it? 16 is Q, 16 is Q, and F is 5. So if you send this message to, this is the message would be sent to this person. Okay, so this is the person whom has this phone number 23157. Okay, CDQ. Now what he will do, this is the ciphertext. So what we'll do, if you get the, if you want to get this plain text, okay, X, let me make it this a B. If I get back this love, this can be done A inverse of B. Okay, so now the task is how we can find it out A inverse. This is really tough for us to find it out A inverse. Okay, here we will be using the mod 26, not the ordinary way of doing the inverse. Okay, so here finding, suppose you are taking the determinant of this matrix. Can anyone tell me what is the determinant of this matrix? What is the determinant of this matrix? Okay, 210. Hello, what is this? Yes, what is the determinant? Suppose determinant, if A is there, if determinant is 1, no issue. Okay, if determinant is more than 1, something is there. Okay, 17 is there. Okay, how we can find it out the inverse, because A inverse is the 1 by determinant of A, isn't it? Adjoint of A. Okay, so determinant of, we need to find out the, what is it? 1 by A inverse. Okay, inverse we need to find it out. How we can find it out? Suppose I'll be taking, suppose I want to find it out. Suppose the determinant is 3. Okay, I want to find it out the A inverse. Okay, A inverse. Okay, so we know this. So whenever you have Z26, let me tell you, set of all integer is divided by 26, which leaves the remainder. All the possible reminders are 0, 1 till 26, till 25. Okay, the set of all integer is divided by 26. The possible reminders are 0, 1, 2, 25. Okay, this is another time we need to spend the what is it? The classes. Okay, integer classes, integer modulo 26, which means that the set of all integer leaves 0, that you can put it the 0 class, 1 class like this. You can, I think you would have studied this at number theory. Okay, so these are the possible remainder when this integer is divided by 26. Here I'll be taking 3 is from 26, Z26, right? I want to find it out what would be the inverse of 3. How we can find it out the inverse of 3? Okay, here suppose A belongs to Z and A inverse is also there, then A into A inverse under mod, this is under multiplication, so would be 1, right? Right, A inverse into A mod some fixed 26. Okay, we need to find it out this one. Okay. Okay. So this, let us take 3 inverse is equal to x. Then what this will be? 3 into x. Yeah. So because a into a inverse, this is equal to 1 mod m, right? Mod n. Mod n. So n is equal to 26. Then this will be 3 into a is 3. This is x. Let us take x. 3 inverse is equal to x. 1 mod 26. Okay. So then bring this 1 this side. 3x minus 1. 3x minus 1 multiples of k, 26, right? Okay. So let us take k is from z. What could be the k can be chosen so that this divides this 3x minus 1. If I choose k is equal to 1, if I choose k is equal to 1, what will happen? 26, bring this 1 this side, plus 1, 3x, and then you can have, what is that? X is equal to 27 by 3. Okay, so you are able to get x. X is equal to, what is that? 9. So inverse of 3 under mod 26 is 9. Okay, so you can have the, what is it, the inverse, what is it, GCD of the number and the 26 should be 1. Okay, so GCD of a comma b is the relatively prime, you know this, a comma b should be 1. This is the co-prime or relatively prime. Okay, or relatively prime. If it is relatively prime, then the inverse is possible, inverses exist. Okay, so this finding the inverse, you can also use the Euclidean algorithm. Okay, so spend a time at the Euclidean algorithm. Okay, Euclidean algorithm, you can spend a time for finding the inverse of the number under some particular mod. Okay, fine. So similarly, we can find it out the reciprocals. For 1 is 1, 3 is 9, 5 is 15, 1 under mod 26. This is the result I'm giving here. Whereas 2, 4, 13 we cannot find because GCD of 4 and 23 not equal to 1. Okay, so 2, GCD of 13 and 26 would be the 13. Therefore, if they are not co-prime, we cannot have the inverse for it. Okay, that we need to understand. Okay, so coming back to the inverse. Okay, so 23, 15, 7. So 17 inverse we need to find it out. So 17, the inverse of 17 is 23. The inverse of 23 is 17. Therefore, you can use 17 is 23, and then under mod 26. So if there is a minus, then you can subtract them. 26 minus 3, 23, 26 minus 15. Okay, 19. So this is the matrix we are taking. Through this matrix, you can find it out the transformation. This is the inverse of the matrix A under mod 26. Okay, 5, 9, 19. CD position is 2, 3. QF position is 16, 5. And then by doing this, we are able to find it out. We can get back the message. Okay, so sometimes you can also make 3 by 3 matrix. Okay, 3 by 3 matrix, provided that inverse, you must have the inverse. Okay. Similarly, ask your friend to create this 3 by 3 matrix and ask her to share only this matrix. You send some message. Okay, you transform this and convert the ciphertext, and that ciphertext you send it to your friends and ask your friend to find it out, and she can find it out this through this A inverse. Like this, you can also play this game. Okay, but here one more information I would like to give you, what you can do anything. Okay, so here you can use some orthogonal matrix under some plane, and I've seen recently one paper, x plus z is equal to 0. Through this matrix, you are able to find it out this is the plane. Okay, for this plane, you can find the basis vector. Okay, you can find the basis. Can anyone give me the basis for this? X plus y is equal to 0. Here, this is your taken x, y, z is from R cube. Okay. Okay. So basis. Anyone? Can you give me the basis? Just I'm telling what you can do, the enhancement of the cipher. Okay. This is the basis. What is that? X, y, z. Here you can assume x is equal to minus y minus z. Okay. So what is that? X is taken as minus y minus z and y z. By taking minus y outside, then what you can have? What is it? minus 1 1 0, and by taking z outside you can have minus 1 0 1. Okay, so this minus 1 1 0 minus 1 0 1, this what is it, generates the entire vector of this plane x plus y z is equal to 0. Okay, now if you want to generalize to the R cube, you can also add some vectors so that it forms a basis for your R cube. Through this basis, find the orthonormal basis through your Gram-Schmidt and those who are doing. For since master students are there, I'm giving this hint. Undergraduate student, no worry about it. Okay, so once you come to the masters, you can take this hint to do research on it. Okay, so what vector can be added so that this forms a basis to the entire R cube. Okay, and for that vector, find the orthogonal basis through the Gram-Schmidt orthogonalization you will be finding, and then you can start to send the message secretly. Okay, but everyone knows this basis, and then finding the inverse is really, that paper was interesting. Okay, I just had a glance at it, but if you are interested, you can also read that. Okay, this is the information that I would like to give you. Okay, fine. Have you understood this Cipher crypto system? Cipher, do you have any doubt in it? Have you understood a little bit about this Cipher, Aisha? I would be using this name Aisha because this name, some name is there, some art, mathematical novel, Aisha Win Inkanidam something. If you are interested, you can see this something 35 pages. That book was there. That was really interesting. Also, Aisha introduced me, therefore I would be using the name. Sorry for it. Okay. Anybody? Do you understand the concepts of Cipher? Shall we go for the next one? Another 15 minutes we can spend it.
Yes, sir.
Yes,
Okay.
sir.
Thank you. Yes. If you have any doubt, any interaction, you are most welcome to do that. 1 minute. If you need, you can. Otherwise, we shall go for the RSA crypto system. Shall I proceed?
Yes, sir.
Okay. Thank you. Okay. Next, let's go into the RSA crypto system. Okay. So this is one of the powerful and mostly used system. It was designed in 1977, whereas the Cipher is done by 1929, 50 years ago. Okay, of introducing this RSA crypto system. Okay, this is done by the three great eminent people: Ron Ristwes, Adi Shamir, and Leonard Edelman. Okay, so therefore this system is named as, by taking their first letter of the name, RSA system. Okay.
Yes,
So
sir.
yeah, this RSA crypto system where
Sir?
yes ma'am.
Sir, you called me, sir. Can you hear me now, sir?
Yes,
Sir, this is Aisha, sir.
yes Aisha.
Okay.
Okay, thank you. We shall interact at last. Okay, fine. So this RSA crypto system, this is completely employed by the number theory concepts, and whereas the Cipher, where the linear algebra and number theory we have used, but here we will be using the congruences, modular exponential, the modular multiplicative inverse, and Euler's functions. These are the things that we will be incorporating at the RSA crypto system. Okay, so at the RSA crypto system, the Euler's phi function should be needed. Okay, so pi n is the number of non-negative integers less than n that are relatively prime to n. Relatively prime, as I said, the greatest common divisor between any two numbers should be 1. So this is the relatively prime or co-prime. This is also called as co-prime or relatively prime. Okay, relatively prime. So suppose n you are taking, how many non-negative integers are there, okay, which are relatively prime to this n. Okay. Suppose pi of 1, let me take n is equal to 1. Okay, pi of 1. Okay, so only 1 is there. Greatest common divisor between 1 comma 1 is 1. Okay. Suppose n is equal to 2. Okay, GCD of pi of 2. Okay, that should be less than n. Okay, the number of non-negative integer less than n. Pi of 2 you are taking, so n is equal to 2. What is that? GCD of 1 comma 2 is 1. So only one such relatively prime exists. The GCD of pi of 2 is 1. So n is equal to 3. Can anyone tell me pi of 3? So you can take GCD of 1 comma 3, okay, 1, and GCD of 2 comma 3, 1. Okay, you should take less than n. Therefore, two possibilities there. Okay, pi of 3 is 3, 2. Similarly, pi of n is equal to 4. Anyone? Can anyone intervene? Pi of 4. GCD of 1 comma 4 is 1. And then 2 comma 4. What is the GCD of 2 comma 4? 2, right? So therefore, this is not a relatively prime. So only this one. And then GCD of 3 comma 4. GCD of 3 comma 4. This is 1. Therefore, two possibilities there. 2. In general, how we can find it out? The number of non-negative integer less than n that are relatively to prime n. Okay, how we can do this? Suppose pi of 7. We need to find it out. How? What is the pi of 7? 7 is the prime number, right? Right? And then pi of 32, pi of 49. Okay, how one can find it out? The number of non-negative integer less than n that are less than 49 that are relatively to prime 49. Okay, how we can find it out? Okay, finding out the relatively prime is really difficult. So for that, and the result is given. Okay, the first one, p is a prime number. So you know the prime number, right? What is a prime number? Anyone? That is
Number which is divisible by 1 and itself.
Is 1 prime number?
No, sir.
Neither prime nor
No,
Yeah,
sir.
neither prime nor
Nor
composite, because it has only one divisor, isn't it? If you want to say it's a prime number, it has two divisor, one and the number itself. Therefore, one is not neither prime nor a composite. Okay, fine. So p is a prime number, then pi of p. Pi function in the sense number of non-negative integer that are less than n, which are relatively to prime n. That's what we have done. If it is p is a prime, then you can have p minus 1 relatively primes are there. Okay, p minus 1 relatively prime. And if you look at this, 3 is a prime number. Okay, then what would be 3 minus 1? What is the relatively prime numbers are there? Okay, for this 3. Similarly, 7. Can you tell me how this, by looking at 7 is a prime number, how many relatively primes are there? 7 minus 1, right? 6. If you look at this, 1, 3, 1, 2, 3, 4, 5, and 6. 1 to 6. All the terms would be there. Okay. So fine. This results you understood. If p is a prime, then pi of p is p minus 1. Suppose if p is a prime and a is a positive integer, then how the pi of p alpha, this is equal to p alpha minus 1. Suppose, let me take, okay, so p is a prime, let me take p is 2, okay, a is equal to some number, let me take, what shall we take, 5, okay, so this will be p of alpha, p of a, this is nothing but what is it, 2 power 5, okay, so pi of 2 power 5, if we have, okay, in this form, 2 power, 2 is the prime number, 2 power 5. If it's so, you can find it out. The number of non-negative integer less than that of 2 power 5 would be, what is that, 2 power 5 minus, this is p of alpha minus 1, I'm sorry, p of alpha minus 1, okay. So this will be 2 power 5 minus 2 power of alpha minus 1, 4, okay, this is 32 minus 16. So therefore 16 numbers are there. Okay, whatever the number you have, that you make it as the prime numbers of the power. Okay, power of the prime numbers 2 power 5. Then you are able to find it out. Okay. This pi function is being used at the RSA Crypto System. This is the reason I'm spending few times here. Okay, if a and b are relatively prime, okay, and the multiplicative, the product of those prime number is n, then pi n would be pi of a and pi of b. Okay, for example, let me take 25, b is equal to 8. Is these two number are relatively prime or not? GCD of a comma b, what is that? That is 25 and 8. What is the GCD of 25 and 8? Anybody?
1.
Yeah, GCD of 25 and 8 is 1. Therefore, they are relatively prime, isn't it? Co-prime. Co-prime or relatively prime. Correct? They are relatively prime. If we do so, then what will happen? You can multiply them. You can take the product of this. 25 and 8s are 200. Okay. So pi of 200, this would be, this is equal to pi of A, pi of 25 into pi of 8. Okay. So pi of 25, you are able to find it out. What is that? How you can find it out? Pi of 25. This can be expressed as pi of pi square, right? You can make it pi number square. This is, you can make it as 2 square. Sorry, 2 power
2 cube.
2 cube. Okay, 2 cube. Okay. So you made it as in this form. What is it? P alpha. So this is nothing but what is it? Pi of 5 square. How would you make this? Pi of 5 square.
Pi square minus 5.
Yeah. Pi of 5 square minus 5. Good. So this is 2 cube minus 2
2
power
square.
2 square. So you are able to find it out. This is 25 minus 5. 20 here. 8 minus 4. What is that?
4.
4 into 4. So 80 numbers are there. Okay. The relatively prime for 20 is 80 numbers are there. So this is how we can find it out for it. Okay. For instance, suppose this is the results you have. Suppose, so pi of something, some number you have, you made it as, you have factorized this in terms of like this. So n you have, this n is factorized as in this form, 2 power 3, 3 power 4 and 7 power 2. Then this can be done it as pi of 2 cube and pi of 3 power 4 and pi of 7 power 2. Then you can use the previous argument and you can do this. This is 2 cube minus 2 square. This is 3 power 4 minus 3 cube, and then 7 square minus 7. Okay. So the given integer n is factorized in this form. Okay. So then finally we obtain this result. If n is a positive integer with the prime factorization, the n is factorized into this prime factorization. Therefore, pi of n would be in this form. So this Euler function, we would RSA crypto system is very well applied. Okay. Now let's go into the RSA crypto system. 5 minutes is there, I can spend here. Okay. Choose any two large prime numbers. So here, the factorizing the prime number, any integer with the prime number is not an easy task. Please understand why they have chosen these two prime numbers. Okay. If I do the product of any prime numbers, okay, you do only your given n. If you're asked to factorize with the prime number, it is really easy. It is not a really easy. It's really difficult. So therefore, here first you have to choose two prime numbers and take the product of these two. Okay, and then compute Euler's pi function, pi of n. So p and q are the prime numbers. Therefore, the factorize is the number of integer, non-negative integer less than n that are relatively to prime would be p minus 1 into q minus 1. This is the argument we have used already. Fine. Third step is over. And fourth step, choose the integer in between 1 and pi. Okay, pi is the number of non-negative integer less than n that are relatively to prime to n. Okay, choose an integer e between e such that the greatest common divisor between e and pi should be 1. Okay, e and pi should be relatively prime. Okay, e and pi would be the relatively prime. This is the fourth step. Okay, and fifth step, here you have chosen e, right? This e, we need to find it out d. This is the inverse of d, is the inverse of e. Okay, we need to find it out the inverse of d. Okay, so that we would be finding by the pi of n through the Euler's pi function. Through the Euler's pi function, we would be finding the e, the inverse of d, inverse of e, that is a d, after determining this. Okay, and then here this n and e are the public key, d, p, q are the public key. So like your mail ID, phone number are the public key, and the password would be the private key. Here d, inverse of e, and then the two prime numbers that you have chosen, that should be kept secret. That is a private key. And here we need to keep all d, p, q and pi should be kept secret. You only reveal your n and e. Okay, you will reveal your n and e. Okay, and e is known as encryption exponent, d is known as decryption exponent. Okay, now at the 6 to 1, the encryption is done. Okay, suppose c is the ciphertext. Okay, ciphertext, and m is the plain text. Okay, m is the plain text. This the message I want to do this to convert into the ciphertext m power e under mod n. Okay, similar decryption. M is the plain text. The plain text can be obtained by doing the what is it, c power d mod n. If you do this, you will be getting this is the encryption and decryption. Let us take an example. Okay, suppose p and q, these are the two prime numbers are chosen, 11 and 3. Okay, and now we need to compute, take the product of this p and q, 33. Okay, first step and second step, and find it out the pi n, number of non-negative integers less than n that are relatively to prime n. Okay, through Euler's pi function. Okay, so p minus 1, 11 minus 1, and 3 minus 1, 2. 10 into 2, 20. Okay, and choose the integer between 1 to 20. Okay, such that the greatest common divisor between e and this pi n should be 1. So here let us choose 3. 3 and 20, the greatest common divisor between is 1. Okay, now we need to determine d. Okay, so inverse of e would be d. This can be done by the modular arithmetic, by the Euclidean modular arithmetic or Euclidean algorithm. Okay, so let us take, suppose this is, just want to do this. What is that? So let us take x is equal to 3 inverse. Okay, so here e is 3. Okay, let me take x is equal to 3 inverse. So we know this 3 into x, 3 into 3 inverse would give the identity 1. Okay, when this multiply under mod 20, right? Okay, let us take x, 3 inverse is equal to x, 3x is equal to 3 congruent 1 mod 26, 20. Okay, and then 3x minus 1 is equal to mod 20k. Okay, 3x minus 1 is the multiples of 20k. So what k can be chosen so that this 3x minus 1 is 3x minus 1 divides 20. So if I choose k is equal to 1, of course k is the integer. So you will be getting 20. 3x, bring this minus 1 this side, 21. So x is equal to 21. 3x is equal to 21. X is equal to what is that? 7, right? So therefore your d would be 7. So inverse of 3 is 7. So this you can do by the Euclidean algorithm as well. Okay, inverse of modular arithmetic. Okay, you determine 7. I mean the inverse of e. And after finding this, you can give the public key. Public key would be n, the product of two prime number, and e, whatever the integer that you have chosen between 1 and pi n. So 33 and 3, this you will be revealing publicly. And the private key would be d, p and q. Okay, the encryption is m power 3, m power e, e is 3, mod 30, n is 33. Okay, and decryption would be c power d, d is 7, mod 33. Okay, so through this we are going to do this. Suppose Reshma wants to send a message to her friend Fatima, email. This is she wants to send. The corresponding numeral value e is 5, m is 13, a is 1, I is 9, l is 12. Consider. Okay, so what is that she can do through this encryption? C m power m is what is it? 5 power 33 mod 33. 5 power 3 is 125. If it is divided by 33, it leaves a remainder 26. Okay, 26. Okay, but here we will be using 1 to 20. Here 1 to 26 such alphabets that we are using. Email z. Similarly, this one. Okay, 13. This one 13 cube 2197 will be getting divided by 33, leaves remainder 19. Yes. Similarly, we will be doing for rest of the term. So she would send this message ZSACL. How Fatima will read? What is it? M plain text. This is equal to what is that? Plain text. This is equal to c power 7 mod 33. Okay. So Z position, she will find the Z position and put it here. Okay, over 7 under mod 26, whatever the answer she obtained, she will read the message. This is the RSA crypto system. Fine. So here, and what we can do something. I know nowadays graph theory plays an important role, right, for doing a research. Suppose you have a message in terms of a graph. Okay, how the graph can be sent secretly, how the graph can be enciphered and deciphered. Such research is going on. The interested people, you can work it out how the crypto system can be done through the graphical graphs perspective. So that you can make it. These are the other applications, graph theory, okay, graph theory and some other, all the data to keep the data secretly. Okay, so here the cryptography concepts are very well used. Okay, so I think I have taken another 4 minutes, more than 4 minutes. So with that, let me stop. And if you have any questions, you can ask. Thank you. And if you look at this cryptography, your linear algebra and what is it, number theory concepts are very well used. Okay. Any questions? If you do not have a questions, I like to interact few things. Okay, fine. So finally, I just want to conclude this. Fermat's last theorem, you know this, x power n, y power n is equal to z power n. Sorry that I'll be taking another 3 minutes. X power n plus y power n is equal to z power n. Is there a solution for this? Anybody? Is there any solution for this Fermat's last theorem? Have you come across? If n is equal to 1, can you give me the solution? 1, 3, 4, right? If x is 1, y is 3, and z would be 4. And if you are taking n is equal to 2, what is that? Any solution? Anybody? Yes? Reshma? What is that? 3 square?
3 square,
4 square?
4 square,
5 square. Yeah. So 3 square, 4 square, 5 square. So we have a solution when n is equal to 2. When n is equal to 3, is there any solution? Any solution for it? Yeah, that's what the Fermat has said. X power n plus y power n is equal to z power n has no solution when n greater than or equal to 3. Okay, this is the Fermat's last theorem. Okay, some 350 years ago, Fermat's posed this conjecture. Conjecture means that has not been proved yet. The statement is true, but it has not been proved yet. That is the conjecture. You know that, right? So a lot of conjecture are there. So even in mathematics, whatever we give the statement, we give the evidence, we give the proof. Even if you tell something about your friend to anybody, they will ask you evidence. What is the evidence? What is the proof that you are saying something about it? Similarly, in maths also, whenever you create a statement, of course the statement is true, but you need to give the evidence. You need to give the proof. If that has not been proved, though it is a true, that is a conjecture. Okay, this is the 350 years conjecture, but it was not been solved until 1992. Okay, in 1992, John Andrew Wells, the English professor, who touched upon this, who gave this. Okay, and in 1992 he gave the proof for this, but still they found the fault in it, and again he gave the revised proof in the year 1996. After 20 years, in 2016, this proof was being accepted, and he was recognized the Abel's Award. Okay, for mathematician, the topmost award is Abel's Award. This Abel's Award was given to the John Andrew Wells. John Andrew Wells. Okay, Andrew Wells. He was given this award, and he was asked by the reporters that how you get this this Fermat's last theorem, because so many great mathematicians, Euler, Commerce, so many mathematicians, Euler, Commerce, and Lagrange's, everybody touched, but they have not generalized They have taken some particular case, n is equal to 4, n is equal to 7. They gave a proof for it, but nobody was able to generalize. Was able to give the generalized proof of it. But John Wells was doing that. Therefore, people asked him, "How you could, though the great eminent people touched upon, they couldn't succeed. How are you able to?" But he said, "I was 10 years old. I was at the library. I was reading these books. I was able to understand this. X power n plus y power n has no solution when n is greater than or equal to 3. At 10 year itself, I was able to understand why I cannot give the proof for it." Always he was focusing and always he was thinking about this equation. Of course, at the tender mind, we couldn't get it everything right. So when he came to college, always focusing on this equation and finding it out. And after becoming professor and along with the scholar, he gave the proof. But it was not still accepted. Still, they found a fault in it. But he was not giving up his confidence. Still, he was sitting along with the scholar and gave a revised proof in the year 1996. And that proof was accepted by everybody. And after 20 years, in 2016, he was recognized with the Sable's Award. And he was telling to the mathematics professors and students, to all the mathematics fraternity, we should not view the equation as an equation. You should view and admire and how you will look at the flower. So each flower is beautiful, right? In the same way, every equation is beautiful. Okay, if you look at that perspective, you can really taste and enjoy the concepts of the mathematics. This is what I would like to tell you, and all the very best. In future, I could find a lot of mathematicians from the Justice Bashir Ahmed College. Okay, so all the very best. Thank you so much for giving this opportunity. So if you have anything, you can interact. Any questions, you can ask.
Thank you very much, sir, for the information in your speech, and the additional reference material you provided were both delicate and timely. We will greatly benefit from your pleasant talk. Thank you, sir, for an interesting talk. Now, if anyone has any questions, I am sure would be pleased to answer them. Anyone have questions?
Sir,
Yes.
how can we further improve our knowledge on crypto system, sir? RSA crypto system.
Yes, my dear, please read your linear algebra number theory. Okay.
Okay, sir.
Okay, that
Thank
is the
you.
base for it. And if you're thorough with it, if it is good at it, as I said, if you have through the plane equation also, a message can be conveyed. Some plane you are taking x plus y plus z is equal 0. From this, find out the basis. And the basis, you can find it out the orthonormal and orthogonal basis. And that matrix you can take. Through this, you can transform the message. You can convey the message like this. Some paper, I think that author was from, you can check it out in the net. Okay.
Thank you so much, sir.
Okay. So how crypto system can be used through the orthogonal matrix. Like this, you can search it and you will be getting.
Okay, sir.
So number three, it's interesting. Whenever you're free, how you're playing with the games in childhood, you would be doing right in lower classes. Like this, you can play with your friends. Give a prime number and ask her to factorize. Give her some integer, ask her to factorize in terms of the prime numbers. The Euler's pi function is really interesting. You can how prime numbers can be factorized. That you can see this. How an integer can be factorized through the prime numbers. Okay, like this you can see this. And anyone, can you give me the largest? Nothing is the largest. Still, it is there. We cannot find the largest till December 2020. The largest prime number would be 2 power of 82. What is it? 8 crores. This is the largest prime number till December 2020. 2 power of 8 crores, 25 lakhs, 80. What is it? Something. 25, something I just forgot. You just see this. Okay, this is the largest prime number till December 20. Okay. And in Robo, the movie called Endiran, and everybody, all the great eminent people were testing the robo, and can you give me the largest prime number? The robo would tell something, it typed something, and it would say, to check whether it's a prime number or not, it will take this, your grand and grandson only can see that, okay, to check whether it is prime number or not. Till then you won't be alive. Our grandparents only would check whether it's a prime number, okay. Such largest prime that robo would give. Okay, that's interesting. You can see that. Thank you. Anything?
So, where will we be using this RSA crypto system?
Everywhere,
Is it only
everywhere.
to read the messages? Or?
Not, my dear. Even if you're sending a message, the message won't go directly. Suppose you are sending an email to anybody, the email won't go directly. The plain text will be converted into the cipher, and then only it will give it to the person. Okay. The encryption, decryption is done there in the mail itself. Okay. Everywhere it is being used to keep the data secret. Everywhere it is being used.
Okay, sir, thank you.
Even voice, whatever you speak, that can be put it in terms of the sequence. Okay, you say something, right? That voice can be put it in terms of the sequence, that can be transformed into some matrix, and then the voice can be changed into some other form. To bring it back, what would be? Where at the signal processing, we can also use this crypto system. It is being used. Okay, so if you're really interested, you please look into that. Definitely, without the base of this linear algebra and number theory and programming language, we cannot do that. Okay, so what are the base that you need? Please work out. As I said, mathematics, be the good at mathematics, but we should also be good at the computer perspective as well. If you're good at both, then really you can do wonders. So please learn any programming language. This is the right age. What we missed when we were students, that you should not. So you can learn any programming language. This is the good time, and you can also do some online courses apart from what you are learning from the classroom. You should learn more and more. Okay, as I said, nowadays the artificial intelligence. Yesterday I was talking with one of my friends. He said, I was telling nowadays IT would be coming back into the original form. He said not IT won't go that much level. Only the artificial intelligence will act more during this. We are at the era of artificial intelligence. Okay, so therefore, if you want to do good at the artificial intelligence, data science, so though we are good at mathematics, if you are not good at the programming language, we cannot do wonders. So please learn any programming language. Yes. Okay, thank you, my dear students.
Thank you, sir. As a token of our appreciation for this time and his valuable contribution, may I call upon Ms. Anisha Sayed to kindly present a vote of thanks to the guest speaker.
Assalamu alaikum wa rahmatullahi wa barakatuhu. A warm and cherished morning to our most valued Honorable Chief Guest, Dr. A. Felix, respected teachers, my dear friends, and all the dignitaries present here. It is my privilege to propose a vote of thanks and acknowledge the contribution of those who worked hard to make this webinar a grand success. First of all, my sincere thanks to the Almighty for making today's webinar a grand success. On behalf of the entire audience, I give a really heartfelt vote of thanks to our chief guest, Dr. A. Felix, who spent his busiest time imparting us with his valuable knowledge. Today, we had the opportunity to hear your thoughts. Thank you, sir, for making time out of your busy schedule and making this webinar invaluable. Your thoughts have enlightened our minds and shown us a new path. I would like to express our sincere thanks to the Honorable Chief Guest, Dr. A. Felix, for giving excellent coverage to RSA Crypto System. I would like to take this opportunity to record my heartfelt thanks to our faculty for organizing such a beneficial webinar. Finally, I extend a very hearty vote of thanks to all the volunteers for making this webinar possible. Last but not the least, I thank all the students for showing their sincere interest in the webinar. I once again thank everyone for making this webinar a success. Thank you.